Imagine a species of deep-sea creature that has only ever detected predators by watching other creatures scream and vanish. They've never seen a predator directly, not once. They've only ever pieced together its existence from the aftermath. The screams, the sudden empty space where something used to be. That's essentially the position modern astronomy is in with black holes, and the more you sit with that comparison, the more unsettling it becomes. We have never detected a black hole the way we detect literally everything else in the universe. Not once. Every confirmed black hole in the history of science has been found by accident, stumbled onto, because something near it was screaming, glowing, or getting torn apart. And that means every method we currently have for finding them only works on the ones that are, in some sense, currently making noise. So here's the disturbing follow-up question nobody likes to answer directly. What about the quiet ones? Tonight, we're going to explain exactly why finding a black hole is nothing like finding a planet, or a star, or a galaxy, and why that fundamental limitation might mean the black holes we've catalogued represent only the smallest, loudest fraction of what's actually out there, drifting silently through the dark, completely unaccounted for. Let's start with the basic problem, because it's baked directly into what a black hole physically is. A black hole forms when matter collapses under its own gravity so completely that it creates a region of space where the escape velocity, the speed you'd need to break free of its gravitational pull, exceeds the speed of light itself. Since nothing in the universe can travel faster than light, nothing that crosses the boundary of a black hole, called the event horizon, can ever come back out. Not light, not radiation, not information of any kind. Every method humanity has ever used to study the universe relies on receiving something. Light from a star, radio waves from a pulsar, infrared heat from a cooling planet. Even the darkest objects we regularly study, like rogue planets wandering without a star, still emit faint traces of heat we can detect with sensitive enough instruments. A black hole, by definition, emits none of that. It isn't dim, it isn't faint. It's a genuine structural absence of information, built directly into the geometry of spacetime itself. You could aim the most advanced telescope ever constructed directly at an isolated black hole's exact coordinates, and you would receive nothing back. Not a weak signal, not a smudge. Total silence forever, unless something else happens to be happening nearby. Which means astronomy has had to solve a genuinely strange problem. How do you build a science around detecting an object that is, by its very nature, undetectable? The answer astronomers arrived at is almost elegant, in a slightly unsettling way. If you can't see the black hole, you look for the evidence of what it's doing to everything around it. Let's walk through how this actually played out historically, because the pattern repeats with almost eerie consistency across every era of black hole discovery. The first strong black hole candidate, Cygnus X1, was found in 1964. Not through visible light, but through X-ray astronomy, a field barely a few years old at the time, born out of instruments carried above Earth's atmosphere on sounding rockets. Cygnus X1 stood out because it was pulsing with X-ray radiation on timescales of milliseconds, a signature that told astronomers the source had to be incredibly compact. Follow-up observation revealed it was locked in orbit with a visible supergiant star, and by studying how that star wobbled, astronomers calculated the mass of its invisible companion. The number was too large for any known stellar object that wasn't already collapsed. A black hole was the only explanation left standing. Notice the pattern already forming. Nobody found Cygnus X1's black hole. They found X-rays, produced by gas, being violently stripped from a companion star. They found a gravitational wobble. They found a mass calculation that ruled out every alternative. The black hole itself was never observed. It was deduced entirely from what it was doing to something else. That same basic structure, find the victim, work backward to the culprit, has defined every subsequent chapter of black hole astronomy since. Fast forward to 2015, and the story gets even stranger, because this time, the evidence wasn't light at all. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected an almost impossibly small ripple in spacetime itself, a distortion smaller than the width of a proton, rippling through two enormous detectors located over 3,000 kilometers apart in the United States. That ripple was the signature of two black holes, each around 30 times the mass of our Sun, spiraling together and merging into one over 1 billion light-years away. The collision itself released more energy in a fraction of a second than the combined output of every star in the observable universe. And because that energy left as gravitational waves rather than light, it produced no visible signal whatsoever. If humanity hadn't built an instrument specifically capable of detecting a wobble in the fabric of space itself, one of the most violent events ever recorded in the universe would have simply happened silently and gone completely unnoticed. We didn't see those black holes. We felt them indirectly as a vibration passing through spacetime. And since that first detection, LIGO and its partner observatories have confirmed dozens more mergers. Every single one found the same accidental way, by catching the aftershock of a collision rather than the objects themselves. Even our most famous, most visually stunning black hole discovery follows this exact same rule, once you look closely enough. In 2019, the Event Horizon Telescope released the first ever image of a black hole, showing a glowing ring of orange light wrapped around a dark, empty center, the supermassive black hole, at the heart of galaxy M87. It was treated correctly as a landmark scientific achievement, but look at what's actually glowing in that picture. It isn't the black hole, it's the superheated gas and matter swirling violently around its edge. Compressed and accelerated to extreme temperatures by gravitational forces, radiating brightly enough for radio telescopes across the planet to detect it. The black hole itself remains exactly what it's always been: a silhouette, a dark absence, defined only by the glowing wreckage surrounding it. Even our most direct, most celebrated photograph of a black hole is still, fundamentally, a picture of everything except the black hole. We've never actually captured the thing responsible, only the damage. So here's where the disturbing implication starts to take real shape. Every single method we have ever used to confirm a black hole depends on that black hole currently doing something dramatic, feeding on a companion star, merging violently with another black hole, distorting light enough to be caught in the act. Every confirmed detection requires activity, which means a black hole that isn't currently doing any of those things is, to every instrument we currently possess, completely invisible. Not faint, not hard to resolve, genuinely undetectable. Astrophysicists call these isolated black holes, and the estimated numbers involved are staggering. Based on how many massive stars have lived and died throughout our galaxy's roughly 13 billion year history, current models suggest there could be somewhere between 100 million and 1 billion stellar mass black holes scattered throughout the Milky Way alone. We've confirmed a few dozen through X-ray binaries, a few dozen more through gravitational wave mergers, most of them well outside our own galaxy entirely. Set that number against the hundreds of millions predicted to exist just within our galactic neighborhood, and the scale of what we're missing becomes almost impossible to hold in your head. We haven't cataloged a small fraction of the black holes around us. We've cataloged a fraction of a fraction of a fraction. Let's talk about why that isn't just a statistical curiosity, because it has genuinely strange, almost uncomfortable practical implications. An isolated black hole doesn't announce itself. It doesn't flicker, glow, or emit any signal from a meaningful distance. It simply exists, its gravity quietly warping the space around it, producing no evidence detectable by any conventional method unless, by sheer chance, we happen to catch it doing one very specific, very rare thing. That method is called gravitational microlensing, and it currently represents almost the only realistic way to detect an isolated black hole that isn't part of a visible binary system. Einstein's general relativity predicts that massive objects bend the path of light passing near them. If an invisible black hole happens to drift directly between Earth and a distant background star, its gravity can briefly magnify and distort that star's light in a precise, predictable, temporary pattern. The catch is almost cruelly specific. This only works if the black hole happens to align almost exactly with the background star, from our exact point of view, during the narrow window when astronomers happen to be watching that patch of sky. It requires an astronomical coincidence layered on top of an astronomical coincidence. In 2022, using years of data gathered by the Hubble Space Telescope, astronomers announced what remains one of the strongest candidate detections of an isolated black hole using exactly this method, a multi-year gravitational distortion event whose mass estimate matched a lone stellar mass black hole, unattached to any companion, drifting silently through interstellar space. It took years of careful, painstaking analysis to make this case, and even now, some details of the mass calculation remain debated among specialists. One confirmed candidate out of an estimated hundreds of millions predicted to exist. That single ratio tells you almost everything you need to know about how far our current detection methods actually reach into the darkness. Now widen the lens even further, because this same blind spot applies to something far larger than stellar mass black holes drifting alone through the galaxy. It applies to the monsters sitting at the centers of galaxies themselves. We know our own galaxy hosts a supermassive black hole, Sagittarius A, roughly 4 million times the mass of our Sun, because astronomers spent decades tracking the precise, whip-fast orbits of stars near the galactic center, watching them loop around an invisible point with a speed only an enormous, concentrated, unseen mass could produce. That took extraordinary patience and extraordinary precision, focused entirely on one single galaxy. Actively feeding supermassive black holes, known as active galactic nuclei, are comparatively easy to spot, because infalling material can glow brightly enough to briefly outshine an entire galaxy's worth of stars. But a quiet, non-feeding supermassive black hole sitting dormant at the center of an otherwise unremarkable galaxy is extraordinarily difficult to confirm without years of dedicated observation aimed specifically at that one galactic core. Multiply that difficulty across an estimated 2 trillion galaxies in the observable universe, and you start to understand just how much of this picture remains, quite literally, unseen, not because these objects are rare, but because confirming even one requires a level of dedicated attention we simply haven't had time to give to more than a tiny handful of galaxies so far. Let's bring this together, because the same thread runs through every part of this story, and it's worth stating plainly. We have never discovered a black hole by simply looking for one and finding it sitting there. Every confirmed detection, from Cygnus X once flickering X-rays in the 1960s, to LIGO's space-time ripples in 2015, to the Event Horizon Telescope's glowing silhouette in 2019, to a single painstaking microlensing event in 2022, required the black hole to be doing something. The instant a black hole goes quiet, it vanishes from our ability to detect it entirely. Our entire catalog of confirmed black holes, then, isn't really a map of what's out there. It's a map of what happened to be caught misbehaving at exactly the right moment, using exactly the right instrument, pointed in exactly the right direction. Everything else, the overwhelming silent majority, remains precisely what it's always been: undetected, patient, indistinguishable from empty space, right up until the moment it finally does something loud enough for us to notice. There's something worth sitting with in that. Something that lingers a little longer than the physics itself. Every black hole we know about because something else paid the price for its discovery. A star torn apart, a beam of starlight briefly bent, space-time itself rippling from a violence powerful enough to finally catch our attention across 1 billion light-years. The quiet ones get to stay hidden, and there is no scientific reason to believe the quiet ones are the minority. Every estimate we have suggests the opposite, that silence, not violence, is the default state for almost every black hole in the universe, at almost every moment of its existence. So, the next time you look up at a clear, seemingly uneventful stretch of night sky, it's worth remembering what uneventful might actually be hiding. Not necessarily nothing, possibly something profoundly massive, profoundly dark, and profoundly patient, sitting there completely unnoticed, not because it isn't there, but because, for now, it simply hasn't done anything yet to give itself away.